Thank you, Chairman. Hi, everyone. My name is Yunhong Ding. I'm from DTU Photonics, Technical University of Denmark. And today, I'm going to talk about the quantum key distribution over multi-core fiber based on silicon photonics, which is together be done with Dr. Davide Bacco, who is sitting somewhere there. And in this talk, I will first introduce our new center, Spock Center, which support this research. And after that, I will talk about the space division multiplexing and why we are using multi-core fibers. And then I will talk why we're also using silicon photonics, and then some implementation of a QKD over multi-core fiber based on silicon chips, including a parallel BB84 protocol and a high-dimensional protocol. And after that, I will summarize my talk. And this new center, which supports this research, stands for Center for Silicon Photonics for Optical Communication. It has 5 flagships headed by Professor Leif. And we are doing nonlinearities, advanced multiplexing, coding theory, and frequency comp generation, and quantum communication. And it's special. This is advanced multiplexing technology and the quantum communication. We have, so in Tango, not exactly correctly, but we have a lot of collaborations. And so we currently have a few activities like OM-based QKD over fiber, and it's a new protocol, so-called DPTS protocol, over 170 kilometers, and which will be presented the poster session, which was supposed to present yesterday, but we postponed it to this afternoon. You're more than welcome to drop by. And also the multi-core fiber QKD, like parallel BB84 and high-dimensional protocol that I will present today. And this communication team, we have 2 professors, Professor Leif and Karsten, and myself, and Davide Bacco, and the 2 PhD students. And as you know, quantum key distribution, everybody knows that it's quite a novel approach to distribute keys with very high security, which can encrypt the classical communication. And then now we can use single photon sources or weak coherent pulses to generate the keys. And we're now can use a one-time pad to encrypt Alice and Bob. We're sharing the secret keys. And there are a few QKD schemes, like continuous variables and distributed phase reference. Also, the discrete variables that we are mostly focusing on this part. And regarding space division multiplexing, so we have to mention in the classical communication, in a big communication community, which is we're really considering this communication capacity limit over a single fiber. As you see here is the current state-of-the-art communication technology for communication capacity over a single standard mode fiber. And using a lot of like WDM, advanced modulation technology, now the capacity has been increased dramatically, and we are expecting that in 2025 we are actually reach the limits of the capacity limits of the standard single mode fiber. And now in the communication community, we are mainly focusing on this so-called space division multiplexing, which in this space, it seems the only dimension has not been explored yet. And then we can have several methods, like use the multi-core fiber, use the mode division multiplexing over this few mode fiber, and also, of course, the OM multiplexing. And which are all very unique method. And they're also in quantum communication, this space division multiplexing has also been applied a lot. And there are quite a few demonstrations. Of course, here I just picked up 3 representative demonstrations. Like here, use the OM-based QKD, use 2 multiple-biased bases. And here is the demonstration by Xinlun's group. They realized the high-dimensional quantum communication using a device-independent scheme. Also here is a demonstration from the Toshiba Center, and then they use this multi-core fiber to communicate both classical and quantum communication simultaneously. And then why multi-core fiber? Then it's compared to the other fibers like field mode fiber and OM fiber. The unique thing of multi-core fiber is it has very low loss with very low crosstalk. Here is the state of the art, the multi-core fiber. Then the typical loss is around only 0.2 dB per kilometer, which is comparable with the standard single-mode fiber. And the crosstalk is even after 17 kilometers long, then the crosstalk is still below minus 70 dB. So this is very unique properties and could be very useful for quantum key distribution. So consider why silicon photonics in the traditional way of this is free space components-based quantum technology. It has demonstrated very successful results. Of course, here is an extreme case of free space components-based quantum system. But the power of silicon photonics is that we could integrate basically everything in a small chip with very large bandwidth, with good stability, and also it's very easy to integrate with the electronics. So indeed, there are quite a few silicon photonics demonstrations for QKD. Like these two demonstrations are from the University of Bristol, and here is another demonstration from University of Toronto. So now people are really looking at this, try to integrate more and more components in silicon chips to demonstrate this quantum key system. And if we need to use silicon photonics for multi-core based QKD, then we need quite a few building blocks. Here we have a few components like laser source, on-chip laser source, MMIs for switches, and automated crosses, and high-efficiency gradient couplers. And based on this, we also have the high-efficiency multi-core fiber couplers. And first, we implemented this simple BB84 protocol over multi-core fiber. So very similar as in this traditional polarization-based BB84, it has two, for each mutual-based basis, it has two states, H and V. If you map this to a core, then you could map H to core A, V to core B. So another mutual-unbiased basis is the base 2, which is superposition of these two cores. And A plus B means you have a pi, you have the same phase between these two cores. A minus B means you have a pi phase difference between these two cores. So if we need to implement this simple protocol to multi-core fiber, then we can define these two cores, A and B of quantum states in the individual two cores. And then in the transmitter side, we need first the VOA to tune the intensity of the pulse to generate decoy states. And then we need to use another MZ Armagen interferometers to split the beams either to A to B or have a superposition of A and B. So in the receiver side, similarly, we have a VOA to balance the loss and also use a second Margin interferometer to detect or receive the quantum states in different bases. And we implemented this experiment over multi-core fiber. And here is the tomography measurement. This is a theory and the experiment. And we got a fidelity of around 97%. And this we also got a QPR of on average of around 4.7% over more than 10 minutes. Of course, this is still limited by the stability of the multi-core fiber, which could be solved by some feedback loop. And currently, the repetition rate is around 5 kilohertz, because this modulation is by the thermal thermal tuning. And of course, you can increase the repetition rates by using high-speed PRN junction or lithium niobate modulators. Then by this, we could, here we have, since we have many cores, then we have in a multi-core fiber. So basically, we could use one pair of cores to implement an independent BB84 protocol. And here is a chip, transmitter chip layout. Then we need to have cascaded Mach-Zehnders to distribute the photons to different couplers, which couples to the multi-core fiber. And in the receiver side, we also need a cascaded Mach-Zehnder interferometers to receive the quantum state for different quantum channels. And as a proof of concept, we just implemented 2 parallel decoy states, BB84 protocol. So here is the tomography, and also the experiment results for the 2 parallel quantum channel. We got 93% and 96% fidelity, respectively. And the BR is for these 2 channels around 5.8% and 4.7%. And since we can transmit quantum states over multi-core fiber. Then next question is why we like to do high-dimensional quantum key distribution. So in classical quantum key distribution is a binary system, which means for each state you can maximum generate 1 bit. But if you increase the state for each basis, then basically for each state it can encode more bits, and the maximum bit is log 2 to n, and is the quantum state in a 1 basis. So first we can gain the so-called photon information efficiency of bit per symbol. So next is regarding the mutual information over quantum beta arrays. If you see the mutual information as a function of quantum beta arrays for different dimensions, you can see that if you increase the dimensionality, then the bound of quantum beta arrays also increases, which means if you go with a higher dimension, you can tolerate more quantum beta arrays, which in turn could potentially increase the transmission distance. And there are quite a few high-dimensional quantum key distribution demonstrations. Here again, the OM-based high-dimensional protocol, and this is the time beam-based protocol very recently in the archive. Also, this is this time and energy entanglement-based scheme in MIT, I think. And over multi-core fiber, then we have to mention that the Xinlun group, they all implement a very similar high-dimensional protocol or multi-core fiber using discrete components. And also in the Korean group, they also use this multi-core fiber for high-dimensional entanglement state generation. And so over multi-core fiber, similarly, if you want to generate high-dimensional quantum states, you need to make superposition of different cores. Here we could, by this combination, we can generate 3 mutually unbiased bases. And for cheap implementation, we need this cheap layout. Again, this is for decoy states, and then this Mach-Zehnder, cascaded Mach-Zehnders interferometers to distribute photons to different cores. And on the receiver side, this also cascaded Mach-Zehnder interferometers to receive in different mutually unbiased bases. So we fabricate the chip in our clean room in D2 DAN chip. So here, here is the fabricated chip, and here is the chip on €1. Of course, it is not the price of the chip, but we really see that it's quite compact. And so here is the tomography measurement for the 3 different bases. We basically got 97 fidelity for the between the experiment and the theory. And here is the final results. So the protocol is Alice randomly choose the quantum state in randomly choosing the basis. The Bob also randomly choose the receiving basis, and in the distillation process, Alice and Bob discard all the data related to different basis choices. And we got on average around I think it's around 13%, which is well below the coherent attack limit and the individual attack limit for high-dimensional case. So if you see a high-dimensional case with a parallel quantum key distribution case, so we have made a comparison. Then if you're in the low noise level, then this in the parallel quantum key distribution case, it can have much higher bit error rate. But if you increase the noise level, then this individual protocol can't survive anymore. Then we can gain much more from the high-dimensional protocol. So in conclusion, we propose to implement highly advanced quantum key distribution over multi-core fiber using silicon photonics, including parallel BB84 and high-dimensional protocol. And we have the first experiment using silicon chips. Of course, it is a proof of concept experiment, but the future, if future is promising, we can use silicon high-speed modulators, also high-speed lithium niobate modulators. Also, the loss, we could use very high-efficiency gradient couplers. Now we have ability to have only 0.6 dB loss gradient couplers. Also, we need to introduce the feedback loop for phase stabilization. And for protocol efficiency, we can use the unbalanced protocol. And hopefully, in having all these improvements, we can target long distance and high rate, high-dimensional QKD system. So with that, I would like to thank you very much for your attention.